तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In our series of lectures on basic electronics, learning by doing, we move on to the next. Before we do that, let us recapitulate what we discussed during the previous lecture. You might recall that we started discussing the various characteristics of an operational amplifier. I listed also the different characteristics which are of importance in using the operational amplifiers for different applications. You can see the input offset voltage, input bias current, input resistance, output resistance, common mode rejection ratio, what is known as CMRR. Then there is a transfer characteristics, then gain bandwidth product, slew rate, or some of the important characteristics we have listed. If you recall the previous lecture, you might remember that we discussed during the last lecture what we mean by the input offset voltage, the definition of the characteristics, and how to measure the input offset voltage, and then the input bias current, the input bias current offset, and also we saw what is the meaning of the input resistance and how to measure the input resistance for a given configuration. So now we will move on to the other characteristics, both the definition and how to measure them in a typical situation. And I will try to show you also a demonstration how to measure these things in a laboratory. Before I do that, I thought I would give you a table of data corresponding to an ideal operational amplifier and a typical operational amplifier, where I have taken the example of 741, which is the most popular operational amplifiers. So if you look at, for example, the input offset voltage, ideally the offset voltage should be 0. You know by now that the input offset voltage is the voltage which I should provide at the input to make the output become 0 when there are no more signals applied. So in principle, ideally the input offset voltage should be 0, but in actual typical 741 operational amplifier, you would find from the data table given by the manufacturer data sheet that this value could be somewhere of few millivolts. In this case, I have listed the typical 1 millivolt value which is given by the manufacturer data book. Similarly, input bias current in principle should be 0, but in real situation, you know, it cannot be 0. It cannot be 0 because the input terminals, they correspond to the terminals of the base of the two transistors which form the differential amplifier configuration. And therefore, the amplifier, if you want it to work like an amplifier, should have some minimum, though finite, current flowing through the base terminals of the transistors. Therefore, it is impossible to have a 0 bias current, even though we list it as the 0 in the ideal case. So, in actual case you would find it will be around few nanoamperes. In this case, in a 741 it is 80 nanoamperes. Incidentally, you can also buy special purpose operational amplifiers which can have this input bias current a very low value of the order of picoamperes or even femtoamperes. Picoamperes corresponds to 10 power minus 12 of an ampere, or femtoamperes 10 power minus 15 ampere. So, you can choose a very low bias current operational amplifier for special applications, but in a typical 741 case it is around 80 nanoamperes. Nano means 10 power minus 9 of an ampere, and it is a very small value for all practical purposes. Then if you look at the input resistance, you can see ideally the input resistance of a voltage amplifier should be infinity. We have seen it several times, so that the input source will not be loaded by the amplifier. Therefore, the input resistance of a good voltage amplifier should be infinity, and that is why the infinity is listed under the ideal op amp situation. But if you look at the situation corresponding to 741, the input offset voltage input resistance is around 2 megohm, 10 power 6 is megohm. So, 2 into 10 power 6 ohms is the actual typical value of the output input resistance in the case of operational amplifier 741. Now, output resistance, if you look at it, has to be 0, because the output of a good voltage amplifier should be almost like an ideal voltage source. But if you look at the typical situation corresponding to the 741, it is 75 ohms, which is rather low, it is very low. So, it is not 0, but still it is a very small value of the order of 75 to 100 ohms. Similarly, CMRR, the common mode rejection ratio, about which I will explain to you in detail this time, should be around infinity, whereas typically it is about 90 dB. That the dB corresponds to decibel. We have also discussed how to look at that. This is something like 80 dB is about 10,000. So, 90 dB is little more than 10,000. Similarly, the gain bandwidth should be infinity. That means the amplifier should be able to amplify all signals from very low level, almost DC, 0 frequency, to very infinite frequencies. But in principle it is not possible even in actual case, and therefore, in the case of operational amplifier, this gain bandwidth product will be about 10 power 6 or close to that. That is what is shown in the table. So, finally, last is a slew rate, about which also we will discuss later. It is about 0.5 volts per microsecond in the case of the operational amplifier 741. So, this I want to just give you so that you get an idea of the numbers corresponding to the various parameters and the characteristics that we talked about. Now, let us move on to the next characteristic which we want to discuss in detail, and that is the output resistance of the amplifier. So, what is the output resistance of the amplifier? For any amplifier, we have already also measured this when we discussed transistor amplifiers, you might recall. So, the output resistance is a resistance as you look from the output terminals into the amplifier. So, when you look from the output terminals, what will be the resistance measured, the Thevenin's equivalent resistance, and that is what is called output resistance. Now, to measure the output resistance, what do we do? That is our immediate concern. So, what we do is we just take one typical amplifier configuration. You can see on the screen, it is a non-inverting amplifier. You have the RF and the RI, and the RI is grounded here, and the input is applied at the non-inverting input, and the output we all know, V output is equal to V in into RF by R1 plus 1 plus RF by R1. This is the gain factor. So, now this is a very simple non-inverting amplifier about which we have already discussed. Now, what I do is I connect a resistance between the output terminal and the ground, that is what I call R, and the arrow shows that it is a variable resistance. That means, the value of this resistance can be varied from some 0 value to some maximum value. Now, what I do is, initially I disconnect this resistance, that means I make this R infinity. When I disconnect this, it becomes infinite resistance, and now I measure what is the output voltage. Then what I do, I introduce this resistance and vary the value of the resistance by using the potentiometer knob until I get a voltage now which is half of what I measured with no resistance present here, that means with infinite resistance. So, if I get half of that value, then I would say the value of the R that I measure here now is the resistance, output resistance of the amplifier. This similar situation we have already discussed with reference to the input resistance last lecture. So, I would perhaps try to explain to you in a simple terms why is it so. Now, if you go on to the equivalent resistance of an operational amplifier, between the two input terminals you have the resistance which is called the input resistance, which we measured last time. Now, on the output side, what you have is a voltage source which is actually having a value of A into V in, where V in is a voltage that is impressed between the two input terminals. A is the voltage gain. In this case, if the no feedback is there, it becomes AOL, the gain with open loop condition. If you have a specific configuration corresponding to non-inverting or inverting, then you can have a finite value of the gain depending upon the choice of resistances in the circuit. So, whatever it is, the output can be given as a voltage source A times V in series with an output resistance RO. So, now what I do, if you now look at the circuit with the external resistance connected, you would find with this, without this resistance, if you measure the voltage using the multimeter M, you would find you will get V naught. Now, after measuring that V naught, I introduce this resistance and I start varying this till I get V naught exactly half of the previous value without altering any of the other input voltage or resistance, etc. So, when that happens, you can see from the equivalent circuit, the voltage source is now connected in series to two resistors RO and R, which is connected outside. If this R is not present, I get VO, which is that actual value of the AV in, the total voltage of the voltage source. The moment I connect an R here, I do get a potential divider. RO and R form a potential divider, and this voltage will be now divided between the two resistors RO and R. So, what I measure in the multimeter will be the voltage that is obtained across the variable resistor R. So, when will this voltage become half of the applied voltage? It will become half only when RO is equal to R. So, that is the principle of this measurement. So, I keep on varying this till I get half the value of the voltage that I measured previously, and at that time I disconnect, that is very important. I disconnect this resistance and I measure its value using a good multimeter, and that value will be the output resistance of the operational amplifier. So, this is the principle of measurement of output resistance. Here you should also remember, I should caution this, I have assumed this voltmeter which measures the output voltage has got infinite resistance or very large resistance compared to the resistances that I have in the circuit. In this case, the output resistance in general will be a very small value. I already mentioned to you in the table the typical value for 741 is 75 ohms, and therefore, this multimeter generally, if it is a digital multimeter for example, it will have a very high input resistance of the order of several megohms, and therefore, 75 ohms when it is in parallel to a large value of resistance, it is as good as 75 ohms. That value will not be affected by the resistance of the multimeter. But if you use any cheap multimeter which is not very well designed, you have to take care that it will have its own resistance, and that will come in parallel with R, and therefore, it can lead to erroneous values. and therefore, you have to be careful to use a high impedance voltmeter whenever you do these experiments. So, here this principle when R0 is equal to R when the output voltage is half of the previous value that I measured. So, this is the principle of the output resistance measurement. Now, I will just quickly show you a simulation of the same, where you can see I have the operational amplifier IC here 741 at the center. I hope you are able to see that, and there is a simple configuration. I have a dual power supply, and I also have a voltage source, and I have 2 multimeters to measure the input and output voltage. I press on the auto setup, then various components will go and sit on in their own, and the circuit will be completed. Right. So, what you have here? You have an op amp connected in with 10, this is around 10K, and this is also 10K. So, I have RF 10K or RI also 10K, and that is connected to the ground. So, and the voltage from the voltage source is connected to the non-inverting input here, and therefore, it is a non-inverting amplifier with a gain 1 plus RF by RI, and the RF by RI is equal to 1 here. Therefore, it is a gain of 2. 1 plus 1 2 is the gain of this amplifier. And now, what I do is I always have large resistance here. This is a potentiometer, and this is having very large resistance. Now, let me switch on the power supply, dual power supply, the voltage source, the multimeters, and now I will apply about 1 volt. I have applied 1 volt from the voltage source at the input, and you see the output is around 1 volt. Right. Now, what I am going to do is I am going to vary this variable potentiometer slowly, and you see what happens to the output voltage, which is measured here. You find the output voltage is now 0.5. So, the previously the measured voltage was 1 volt, and now it is 0.5 volt. That means, it has become V0 by 2. The output voltage is half of the input voltage, and at that time I should know what is the resistance that I have included in the circuit in the variable resistor. For that, I have to disconnect this resistor, and I should make the voltmeter into a resistance meter, ohm meter, and measure at the terminals of these after disconnecting from the circuit. That is what I am going to do by pressing measure resistance. You can see all the other things have been removed from the screen, only the potentiometer is there, and the 2 terminals of the potentiometer are connected to the voltmeter, which is now measuring ohms, and you see a reading of 80 ohms. So, that gives us the output resistance of the operational amplifier. So, having shown the simulation, now I would like to show you an actual measurement done on the laboratory table. So, here you can see the circuit diagram shown on the top, and there is a breadboard at the bottom. In the circuit diagram, we have used 10 kilo ohm as RI and 100 kilo ohm as RF, and therefore, there is a gain of 1 plus 100 by 10 approximately 11. So, and the input voltage is given at the non-inverting input, because it is a non-inverting amplifier, and you can see I have connected a potentiometer. I will measure. I have not connected the potentiometer, it is still here. Now, I will switch on the multimeter. I have given 200 millivolts from the voltage source. This is the voltage source you are now familiar with, we have seen it several times. This 200 millivolts input is given at the pin number 3 corresponding to the non-inverting input, and the output is measured using the multimeter at pin number 6. And if you look at the multimeter, it shows a value of 2.18. So, 200 millivolt multiplied approximately by 10 is 2 volts, 2.18 is what I get. Now, without disturbing any of the voltages, I should now connect the variable resistor, which is here. This is the variable resistor. It is actually a 10 turn potentiometer. If you perform 1 turn, the value will be usually in our normal potentiometers, if you just rotate by nearly 360 degrees, all the resistance variation would have been made. In this case, you have to rotate 10 times the spindle to make the variation possible for the whole range, and therefore you can do it in much smaller increments of resistance. That is why I am using it. Now I am going to connect this quickly into the output terminal. So I have now connected the potentiometer, and you can see if I vary that, the output voltage in the voltmeter is changing. The output in the, you observe the output as, and as I keep changing now, you can see the voltage is increasing. Now it is decreasing, it is 1.85 and it is still decreasing. I keep on increasing the voltage slowly, and when it comes to about 1 volt I will stop. It is now 1.34, it is 1.1, so it is about 1.02. So now I have stopped this. Previously it was about 2.18, so maybe I can make it 1.09 or 0.7, okay, 1.08. Now it is half the value that I measured previously, 1.08. At this stage I should disconnect this resistance. So I will connect it to a different area in the breadboard, and I also change the meter to measure resistance. I have converted the voltmeter into a resistance meter. There is 200 ohms range, and I am now measuring the resistance by disconnecting from the circuit, putting into a independent area, and then I measure the value of the resistance is 49.8 or so, nearly 50 ohms. So that 50 ohms is the output resistance of this 741 that I have used in the circuit. In the typical table you saw the value should be around 75 ohms, and 50 ohms is actually a good value. Okay, having seen how to measure the output resistance of an operational amplifier by actually performing an experiment, let us move on to the next characteristics in the table, and that is what is known as common mode rejection ratio, or CMRR. It is called CMRR. This common mode rejection ratio is actually an important characteristic of differential amplifiers. Now in any differential amplifier, this parameter becomes an important one. What do you mean by, before we go into the actual definition of CMRR, it will be good to know how a differential amplifier can be considered in two different modes corresponding to differential mode and common mode. So if I now apply a signal between the two, say, input terminals, then this becomes the differential signal which is being applied to the operational amplifier. So this is called a differential mode of connection. Instead, if I connect the two inputs together, shorting them, and then apply a voltage between the ground and the point, then it becomes, this signal becomes common to both the input terminals, and therefore it is called common mode. So this is the differential mode of connection, this is the common mode of connection. In the differential mode of connection, VOD, that is the differential output voltage, is equal to AD, which is called the differential gain, into VD, the input differential voltage you apply in the differential mode. So VOD is equal to AD into VD is corresponding to this configuration. Similarly, for the common mode, VOC, the voltage output corresponding to the common mode configuration, is equal to AC, the common mode gain, multiplied by Vc, the common mode voltage applied at the input. So you can see we now talk of two different gains. One is called the AD, the differential gain, and the other is called AC, the common mode gain. So in principle, a differential amplifier can be associated with two different gains corresponding to AD and AC. But in actual practice, you would find you would be giving to the two input terminals of an operational amplifier typically one voltage source corresponding to Vi1 and another voltage source corresponding to Vi2 independently. without either connecting them together or connecting the voltage source between them. In that case, how do we obtain the Vd and the Vc, the differential inputs voltage and the common mode input voltage? You can always see if Vi1 and Vi2 are the two input voltages, Vd is nothing but the difference between the two, Vi1 difference Vi2, depending upon which is larger you will get either a positive or a negative value here. So, this can be the way which is the most practical way of looking at Vd, and similarly for Vc, for the same situation where I have applied Vi1 for one terminal and Vi2 for the other terminal, Vc common mode will be given by the average of these two, which is the common for both the input, half of Vi1 plus Vi2. So, now that we know there are two different modes, there are two different gains that one can talk of, and how to obtain from the two independent voltages that you connect at the input terminals of an operational amplifier, how to get the Vc and the Vd. Having got that, now you can see what is the total output. In principle, this whenever you connect at the input Vi1 and Vi2, output will be Vo, but that output voltage will have contributions from the common mode voltage as well as the differential voltage. So, V output in principle is the combination of Ad into Vd, where Vd is the differential voltage, and Ac into Vc, where Vc is the common mode voltage, and Ad and Ac are the differential and common mode gains. So, this is a general expression for the output of a differential amplifier, and Ad and Ac are the differential and common mode gains. Okay, having explained about all these things, it is very easy to define now the common mode rejection ratio, which is actually defined by the differential voltage gain divided by the common mode voltage gain. So, what does it say? CMRR, it tells you how much is the differential voltage gain larger than the common mode gain. The value of the CMRR is normally expressed in decibels using logarithmic definition. CMRR log is equal to 20 log to base 10 Ad by Ac in decibels. So, for example, typically for 741 this CMRR is 90 dB. I already mentioned to you, I also showed you at the in the table at the beginning of the lecture. So, that 90 dB will correspond to nearly 10,000, little more than 10,000, and that means what? The differential gain will be 10,000 times the common mode gain. Okay, the ratio is 10,000. That means the operational amplifier has got some special preference for differential gains than the common mode gain. It does not give importance to the common signal, but it gives importance only to the differential gain. This is a very important characteristics, as I already mentioned to you, because most of the time for every amplifier, whenever I use in the any situation, you would find there is always enormous sources of noise voltages all around us. For example, the 50 hertz voltage, the radio frequency from the different television stations and things like that, all around us there are a lot of electromagnetic waves present from different sources, radio stations, television stations, and communication lines, etc. And therefore, all of them, they will be very small in magnitude, I agree. Even then the amplifier will not be able to distinguish them. In principle, it will also be amplified. All these noise voltages also will be amplified along with the signal, which is the only thing that you want to concentrate on, and therefore the output will have enormous voltages coming from these noise voltages. Sometimes the noise voltages can completely swamp the signal that you wanted to observe. Then the signal will get buried in noise and you will not be able to see the signal very clearly. Therefore, if I have a good CMRR, if I use a differential amplifier as the first stage, and if that differential amplifier has got these characteristics, which is called common mode rejection ratio, CMRR, very high, then you can see the amplifier will reject all the signals which are common to both the inputs very well, efficiently, and therefore all the signals which are common to the two input terminals are basically the noise voltages all around us, and therefore you would find it will be very good noise rejection characteristics. and what you get at the output will only be corresponding to the signal on which you are more interested. So, that is the reason why CMRR is a very very important characteristics of any differential amplifier and in particular operational amplifier. Right. So, if I say, I have given a typical example on the screen, if that op amp CMRR is about 100 dB, then it corresponds to 10 power 5. For every 20 dB there will be a decade, and so 100 dB will have 5 decades, and therefore it will be 10 power 5. Therefore, the differential voltages will be amplified nearly 10 power times more than the common mode signals. That is what it says. The CMRR of 741 is 90 dB, which is about more than 10,000. For there are some amplifiers which are called instrumentation amplifiers, which are meant for applying to very low level signals. When you are trying to amplify very low level signals in the microvolts and nanovolts range, you would find the noise voltages also can be of the same magnitude, and therefore they can really harm the signal at the output. If I use a good instrumentation amplifier, which is a high gain differential amplifier exclusively made with very large value of CMRR, then you would find the rejection of the noise will be very efficient. And for example, there is one op amp called 725, and the value of CMRR for 725 is 120 dB, because it is an instrumentation amplifier, and that means it is 1 million times more. The differential gain, it is about 1 million times more than the common mode signal. Okay. Now, what I want to do is, how do we get in principle the AD and the AC? To measure AD, I can now set my VI1 is equal to minus VI2, and that is equal to 0.5 volts. So, I keep VI1 is equal to VI2 except for the opposite polarity. So, it is 0.5 volts plus and 0.5 volts minus, and therefore, what will be my VD? VD is VI1 minus VI2, 0.5 volts minus 0.5 volt, that is equal to 1 volt. And what is my VC? VC is half of VI1 plus VI2, average of the two input, half of 0.5 plus minus 0.5, and that is, this becomes 0, and therefore VC is 0. So, what I have is VD is equal to 1 volt, VC is equal to 0, therefore, we output V0 now is equal to AD VD plus AC VC. We have already seen AD into 1 volt plus AC into 0 volts. Anything into 0 is 0, and therefore AD into 1 volt is AD. Therefore, if now I measure what is the output voltage, that in magnitude gives me the differential gain straight away. So, that is one way quickly to measure AD. Similarly, if I want to measure the AC, then I set VI1 is equal to VI2 is equal to 1 volt, then VD is equal to VI1 minus VI2, the 1 volt minus 1 volt will give me 0, therefore there is no VD, and VC is average of half of VI1 plus VI2, that is equal to 1 volt, and that output voltage, therefore now AD into 0, because now VD is 0, plus AC into 1 volt, therefore it is AC. So, if I give 0.5 and minus 0.5 for the two inputs, I get the output voltage in magnitude the AD. If I give 1 volt and 1 volt at the input, I get AC as the voltage at the output. So, this is one simple way it looks like to measure AC and AD. Once you measure AC and AD, you can get CMRR, which is equal to AD by AC from dividing the two. But unfortunately, in practical situations, you would find it is very difficult to set very precisely 0.5 volts and 0.5 volts, because the 0.5 volts should be very precisely 0.5 volts up to 3 or 4 decimals, because the gain could be very high, and therefore the output voltage can be very different, even if there is a very slight difference between the two input. Only when I make both the inputs exactly equal using two sources, I will be able to do this type of a measurement. So, in principle, in practice it is going to be very difficult. So, we will use other techniques to measure the output voltage. So, now I want to try to impress upon you the concept of the CMRR in a much more clear manner by giving another simple illustration. So, let us assume that I have an amplifier with a gain 10. Of course, it is not a very large gain, but it is only 10, and I have Vi1, Vi2, I give 0 for Vi1 and I give 100 millivolt for Vi2. So, what I expect 10 into the difference between these two is 100 millivolt. If it is a good differential amplifier, it should only worry about the difference between the two inputs. So, if I have 0 and 100 millivolts for the two inputs, the difference is 100 millivolt. That multiplied by 10, the gain is 1000 millivolt, which is nothing but 1 volt. So, I must get only 1 volt at the output, and the common mode signal is 0 here, here also it is 0, and therefore, that is the average value is around 50. So, that will be 50 into 10, 500 millivolt, that is what I will get. Now, let me say when I in a typical situation I give 0 volts here, 100 millivolts, I get 1 volt, and then what I do is I modify, I give 1 volt at the input V1 and 1.1 volt at the input V2. What do you mean by 1.1? It is 1 volt plus 100 millivolt. This is 1 volt, one input is 1 volt, the other input is 1 volt plus 100 millivolt. The difference is still 100 millivolt. So, if the amplifier is a very good amplifier, difference amplifier, then it will now worry only about that 100 millivolt, which is the only the difference between the two inputs, and that multiplied by 10 volt, if I get 1 volt, that means this type of amplifier is not at all worried about the signal which are common to both the inputs, whether it is 0 and 100 millivolt, or whether it is 1 volt and 1.1, or it is 5 volts and 5.1, whatever, the output voltage is 1 volt, which is just nothing but the difference in voltage multiplied by the gain. 100 multiplied by 10 is 1 volt, and that is the constant irrespective of what is the common voltage that I have for at the two inputs. If an amplifier can show such a characteristics, we call that amplifier an excellent amplifier, an ideal amplifier, and the CMRR in this case can be infinity. Okay. It is completely able to reject all the common voltages, it is only amplifying the difference in the two signals. But I already mentioned to you, in reality you would find it is very difficult to get such CMRR, high value CMRR. You can with great difficulty get 90 dB or 100 dB, etc. Therefore, let us now look at some small modification, algebraic variation of the output voltage. Output voltage is equal to AD Vd plus AC Vc. If I take this AD Vd common outside, it becomes 1 plus 1 by CMRR into Vc by Vd, because AD by AC is CMRR, it is coming in the denominator, therefore 1 by CMRR Vc by Vd. So, this formula is useful in doing some simple problems, therefore, I am trying to indicate to you. So, I have also given an example here. Determine the output voltage of an op amp for input voltages Vi1 is equal to 150 microvolt, Vi2 is equal to 140 microvolt. The amplitude has a differential gain of AD 4000 and the value of CMRR is 100. Assume it is 100 and then B assume it is 10 power 5. So, what happens, let us see. The two inputs are 150 and 140. So, Vd is 150 minus 140 microvolt, and therefore, what I get is 10 microvolt, and the common voltage is half of the two inputs. So, 150 plus 140 by 2, that will be 145 microvolt, and output voltage is AD Vd into 1 plus 1 by CMRR Vc by Vd. So, 4000 multiplied by 10 microvolt, which is the differential voltage, 1 plus 1 by 100 for the first case, the CMRR is 100, and 145 by 10 microvolt, if you calculate, it is 45.8 millivolts. If you take the second case where it is 10 power 5, you would find 4000 into 10 microvolt is the actual voltage you should get, 40 millivolts, but you are getting 45.8 millivolt in one case, because the CMRR there is smaller or only 100. When you have CMRR 10 power 5, you find this value becomes 40.006. That means, if the CMRR is a very large value, then the output voltage is almost equal to the 4000 multiplied by 10 microvolt, that means AD into VD. The contribution from the second term will almost be very small. That is what we try to understand from this example. So, when the CMRR is high, it becomes a very good differential amplifier, which is always concerned only between the difference in the two inputs, and it is not so much worried about the common signals. Right. How do we actually measure CMRR in the laboratory? That is our next problem. So, for that you can immediately tell you can tell me that we have to measure AD and we have to measure AC. So, let us see how we can practically do this in the laboratory by measuring the AD and AC. I have given you two circuits on the screen. You can see this is a differential amplifier. I have used 10K and 100K in the feedback, and again 10K and 100K. This is a differential amplifier configuration. We have not discussed this yet, but we will discuss it shortly in one of the lectures later. But for the present, you can assume this to be a differential amplifier, and therefore the VD here is Vi1 minus Vi2 that we already know, and I will measure what is the output voltage. I will give one voltage here, I will give another voltage to the other input, I will find out what is the difference, and I will measure what is the output. Output divided by the difference in the two input will give me the gain corresponding to the differential amplifier AD. This is a very simple measure. Then if you want to measure common mode gain, then what you do is you connect the two input terminals together and connect a voltage source together. This is a common mode configuration we already discussed. So, now measure what is the output for the same amplifier and divide the output by the common mode input signal, and that will give me what is the AC, the common mode gain. So, this is a simple practical way of measuring the AD and the AC. Once you measure AD and AC, you can divide one by the other and you can obtain the common mode rejection ratio. Now, I will take a typical numerical example here, which is similar to what I would be doing later on in an actual demonstration. So, what I have done is I have applied Vi1 to be 0.5 volts and Vi2 is slightly different, that is 0.48 volts. So, what is the differential voltage? 0.5 minus 0.48, and that is 0.02 volts, or in principle it is 20 millivolts. So, the differential voltage at the input terminal of a differential amplifier is 20 millivolts, and the gain is 10 here, 100K and 10K. Therefore, the output voltage, if I multiply by 10, it will be 200 millivolts. AD into 20 millivolts is 200 millivolt. Therefore, I can find out what is the AD. AD is 200 by 20 is 10. So, by measuring the output voltage, which is 200 millivolt, and measuring the input difference, which is 10 millivolt, 20 millivolt, I know 200 by 20 is 10, and therefore I know AD. Of course, we know from the number of resistors that I have used, value of the resistors, it is also 10 in this case. But in principle, even if you do not know, by measuring the output voltage and the difference in the input voltage, I can directly divide and obtain the value of the differential gain. In the second case, I have connected the two input terminals and applied 0.5 volts constant. Now, what is the output voltage? I measured 0.002 volts or close to that. So, what is the gain? Voltage output divided by the voltage input, 0.002 divided by 0.5 and the 0.004 volts. The gain is 004. Therefore, I have now got the AD, which is 10, and AC, which is 0.004. That means it is a very small value. The common mode gain is small value. It is not an amplifier at all, it is actually an attenuator. It has reduced the output voltage. So, CMRR is AD by AC, and that is 10 by 0.004, and that is around 2500 or so. And if I convert it into dB by multiplying 20 log 2500 to base 10, you would find it is around 68 dB. The actual typical value for 741 I said is around 90 dB. So, it is about 70 dB what we measure here typically. So, it is possible in a laboratory to actually perform this experiment and measure the CMRR for the operational amplifier, which is what I am going to do now. I am going to show you a demonstration. Here you can see I have got the two circuits which I just discussed. This is in the differential mode, so that there is a separate Vi1 and a separate Vi2 in the circuit, and here is a common mode signal. I have connected the two input terminals together and applying the voltage here. So, I am going to do these two and measure the output in each case and measure the output by the difference in voltage in this case, that will give the AD, measure the output and the corresponding input here, that will give me AC, then I will divide one by the other to obtain what is the CMRR, right. So, I have used one of the voltage source VI1 0.5 here, this is actually 500 millivolts corresponding to 0.5 volts, that is connected to one of the input terminal, and I have used one of the power supply which is not being used here, a variable power supply, that output voltage you can see around 0.5, it is actually 0.49 or so, so 48, and that is what is given here. Now, what I can do is I can first use the multimeter which is here, I will connect the multimeter to the two inputs and measure what is the voltage here. So, I will ask you to concentrate on the voltmeter while I connect to the two inputs. Now, I take the multimeter and connect to the input terminal, one input terminal, you can see it is 0.5 volts, that is V1. Now, I take it out and connect to the second input, and it is 0.48 or so, 0.479 or 48. So, the difference is 0.5 minus 0.48, it is 20 millivolts, and therefore, now I take it out and connect it at the output terminal. So, the value of voltmeter is 200, therefore, 20 millivolts is the difference multiplied by the 10 which is the gain of the amplifier is 200, therefore, that is what we got at the output. So, this gain, differential gain is 20. Now, what I am going to do is I am going to remove these two input voltages and connect the two input terminals together and connect one voltage, one of the 0.5 volts alone. Now, you can see there is a red wire which has come in the circuit which is actually connecting the two input terminals V1 and V2, and there is only one source with this source which is connected at the input, and this is already 0.5. I have not changed anything here, therefore, 0.5 volts is given at the input, and what is the output voltage? The output voltage is 0.456. So, this is 0.456. So, the gain is nearly less than 1. This is 0.5 and this is 0.56. So, the output voltage is nearly 0.008 or 009. So, it is a very, very low value, and therefore, 0.5 divided by 0.009 is a AC, and it is going to be very, very small, and then we already saw the differential gain is 10. So, this voltage 0.009 divided by 0.5 is about 0.002, and therefore, you will get around 5000 as the CMRR. 5000 will be the CMRR, and if you look at the dB, this will be nearly 80 dB, close to say 80 dB, 75 dB or so. Okay. So, we saw how we can measure in the laboratory the CMRR, and now we will move on to the next characteristics, which is basically the transfer characteristics of an operational amplifier. This is also a very important characteristics, and what we mean by that here is, if I have an input and an output, what will be the graph between the input and the output. So, the transfer characteristic is a graph plotted between the input and the output of the op amp. Since basically it is a differential amplifier, Vi is equal to V1 minus V2, the difference the two, and V output is AOL, the open loop gain, multiplied by the difference. So, but the AOL, the open loop gain of an operational amplifier, is typically 10 power 5, 100,000. So, if we give Vi to be 1 volt, then what will be the output? The gain is without any feedback. VOL means, AOL means what? Open loop gain. Open loop gain means there is no feedback. So, if I have that, you would find the output should be 10 to the power of 5 volts. Can I get 10 to the power of 5 volts at the output by giving 1 volt? You can never get, because the output voltage can never be greater than the power supply voltage, and the power supply voltage is only plus 12 volts or minus 12 volts, because it is a dual supply. And therefore, you would find the output voltage whenever it exceeds by the simple formula VO is equal to AOL by VI, when it exceeds 12 volts, it will saturate at 12 volts. So, for all higher values of voltages at the input, the output voltage will remain constant at plus 12 volts, and it will not increase beyond that. Similarly, for the negative side, and therefore, you would find there is a limit to the output voltage corresponding to plus or minus 12 volts or plus or minus VCC as we call it. So, that shows what will be the limit of the input voltage. The limit at the input voltage should be plus or minus 12 volts, which is the limit for the output voltage, divided by the gain gives me the input voltage. So, plus or minus 12 volts by 10 power 5 gives me plus or minus 120 microvolt. I have multiplied numerator and denominator by 10. So, it is about 120 microvolt. That means what? An operational amplifier will obey the equation V output is equal to AOL into VI only when the input ranges are between the two input terminals, the voltages are plus or minus 120 microvolt or less. Whenever it exceeds 120 microvolt or more, the output voltage will saturate either at the plus or minus, depending upon which polarity of the voltage is higher. So, this is what we call the transfer characteristics of the operational amplifier. I have shown a graph here. This is a V input and this is the V output, the vertical line, and you can see at till 120 microvolt there is a linear relationship passing through the origin, which corresponds to the amplifier behavior, and beyond that 120 microvolt the output voltage remains constant at plus 12 volts on the positive side, and the negative side it remains constant at minus 12 volts. So, we are using operational amplifier in all the applications that we are going to discuss as an amplifier confined to this small range where the difference between the two input terminals at the op amp is plus or minus 120 microvolt. So, this graph that you get is what is known as the transfer characteristics, and it is a very important characteristics. Now, if you look at the slope of this line, the slope of the line will be the gain, open loop gain of the operational amplifier, 10 power 5 in this case. Now, if you look at the point going through the 0, if it is perfectly going through 0, that means it has got no offset voltage. When the input voltage is 0, the output voltage also is 0. So, but in principle, you know, we already saw for a typical real operational amplifier, this is not the case. You will have a small offset voltage, and therefore, this will not exactly pass through the center, only in an ideal case it will pass through the center. So, this plus or minus 120 microvolt limit is very important to remember. Therefore, because this is a very small value, in all practical operational amplifier, if it is working as an amplifier, if you measure the voltage between the two input terminals, it should be almost the same. The difference should only be, if for example, if I measure at one input terminal 1 volt, the other input terminal, if it is an amplifier configuration, cannot be other than 1 volt plus or minus 120 microvolts, and therefore, both the terminals, so the voltages should be same if the operational amplifier is performing as an amplifier, and this is a very important thing to know, especially when you are doing troubleshooting. When an operational amplifier is not working, it is configured as an amplifier and it is not working, you want to know what is the problem with the circuit. So, all that you have to do is first measure, see whether all the voltages are coming properly at the VCC, plus VCC and minus VCC at the pins of the operational amplifier, and then you should find out whether at the two input terminals the voltages at V1 and V2 are very close to each other, almost same, plus or minus 120 microvolt, and that if that happens, that means the operational amplifier is in good condition. If you find the two voltages are different by more than 1 volt or 0.5 volt or whatever, then you immediately can conclude there is something wrong with the either operational amplifier or any of the connections around it. So, you can analyze them in much more detail and find out what is wrong in the circuit. Now, I will perhaps in the next lecture I will briefly touch upon this transfer characteristics, and then I will also show you a demonstration of how to measure the output transfer characteristics. I already mentioned to you the transfer characteristics will be very useful in several applications like the comparator. There are a lot of applications related to the comparator. I will also therefore show you the transfer characteristics using an oscilloscope, and then we will discuss the other parameters and the characteristics of the operational amplifier. Thank you.